The warm-up question for today says, which shows a wavelength, and it shows images of 4 different waves or portions of waves, A, B, C, and D. And then we have a couple of follow-up questions about the wave that's in that red box at the top. But looking at this, which one of these is going to represent one wavelength, A, B, C, or D? What did we say? What do you? C. Good, yeah, C. Okay, if you're looking for a wavelength, again, you need to find one full wave cycle from between 2 points that are in phase with one another. We learned that term yesterday. And so you need to, in this case, C starts at equilibrium, and it includes a full wave cycle because it goes through a crest, through a trough, and then it returns back to equilibrium again. Okay, and so yes, that's going to be your full wavelength there. Number 2 says, if the waves boxed in red occur over a time of 9 seconds, what's the period? Okay, again, you need to remember what period is. Period is the time it takes for one wave. So it's not the time it takes for all of those waves in that box, but rather just one. Okay, so I know that there's more than one wave in that box, so I know that the period's going to be less than 9. Okay, because each one's going to take some fraction of that 9 seconds. If I take a look at the waves in this red box and I count them, there's one wave ends right here where my red cursor is. The second wave ends right here, again where my red cursor is. There are a total of 3 waves here. Okay, if it takes 3 waves 9 seconds, how long will it take one wave? 3 seconds, that's your period. Okay, so the answer to the second question is 3 seconds, and you can see exactly how we did that. You can do this mental math really easy, but it's just 9 divided by 3. It's the total time divided by the total number of wave cycles. That will give you your period, or the time per wave. Frequency, again, you need to remember that frequency is inversely proportional to period. So if you find period, it's really easy. You can just do, and I have the equation on the board over there, frequency is 1 over t. Or you can go back to the definition. Okay, frequency is the number of wave cycles per second. So instead of dividing 9 by 3, I would instead be dividing 3 by 9. Or, again, 1 over t, 1 over 3, 1/3. Either way, 3 over 9, 1/3, same thing. My frequency is 0.3, repeating, 0.33333. The unit for frequency is hertz, which means that is the number of cycles per second. Okay, that is what hertz is an inverse second, so it's per second. But those are your answers to the warm-up question, and a just real quick review over some of these things yet again, just to make sure we're not forgetting how to deal with each of those numbers that we associate, those measurements that we associate with our waves. Does anybody have a question about the warm-up? Okay. Then we're going to jump into some notes today. I told you yesterday that we're going to be talking about wave behaviors, and yesterday we focused primarily on reflection and then the interference that occurs when that wave reflects. So we're going to kind of just do a quick recap over that, and then we're going to jump into those other wave behaviors that were mentioned yesterday, and then we'll have an assignment at the end of the period. So again, to kind of go back to yesterday, we talked about wave interference, which occurs when 2 waves meet while traveling in the same medium. That could be 2 sound waves while traveling in the same room. You could have interference, or you could look at it just in a string, a really simple example like what you did in the FET. But we talked about 2 different types of interference, constructive interference and destructive interference. And you need to remember the difference. You're going to have constructive interference when the displacement of your medium is in the same direction. That means that a crest overlaps with a crest, or a trough overlaps with a trough, but you're going to have that displacement in the same direction as those waves overlap in that medium. And when that happens, the waves build on each other, so you add their amplitudes together. Again, if you think constructive, or maybe you're thinking construction or building, okay, so that may help you remember that definition, but they're going to add together, they're going to build on one another. Destructive interference, on the other hand, is going to happen when your displacements are in opposite directions, so you have one wave that's displaced or has positive displacement, like a crest, and another that has negative displacement, where a trough is, and those happen to overlap at the same point. And so then you're going to have them cancel out, maybe just partially. if they're not the same size amplitudes, or maybe entirely if the waves have the exact same amplitude and the same wavelength. But that's going to be destructive interference. They're going to destroy, or they're going to be destructive toward one another. They're going to cancel each other out. And of course, when you do that, you end up subtracting. You're really adding the amplitudes. It's just one of them is going to be negative. So you're adding a negative there. That's why it says subtract the magnitudes, or again, you can add them together with the sign. We did this yesterday, so hopefully this is sounding familiar because it shouldn't be new. So I've got 3 different points here labeled A, B, and C. I want you to take a moment to just look at this and determine on your own or by discussing with your neighbor whether each of these points would represent a point in time where you have constructive interference or where you have destructive interference. So take a moment to look at them and see if you could answer each one, because I might call on you, so make sure you have an answer ready. And whether point B, and point C represent constructive interference or destructive interference. So go ahead and take 17 seconds, and I'll call on somebody to share. So again, talk to your neighbor if you're not sure. All right. Hopefully that was enough time for y'all to talk about it. Jumai, what did you ladies say back there? What for point A? Is that going to be constructive or destructive? Constructive. Constructive, perfect, because they both have a positive displacement of the medium. I don't know, it's not necessarily at the crest, but they're both on the positive side. Okay, so that would be constructive. Okay, what about at point... and you can see them add together here. But at point B, what did you guys say, Nate?
Destructive.
Destructive. Again, I have positive amplitude with the red wave and negative with the blue wave. Perfect. Those are going to be destructive. Okay, what did you guys say about point C, Callie?
Constructive.
Okay, constructive. They are both in the negative direction, but they're still going to add together because they're going in the same direction. And here is the resulting wave front that you get as these two overlap. You can see the points where they're constructive. You end up with even higher crests or even lower troughs, like here and here at points A and C. And point B, it's almost back to equilibrium again because they're canceling out almost entirely, not quite, but almost entirely canceling out at that point. Okay, so again, be able to identify those. With our transverse waves, that's a little bit easier, but I could also ask you about interference with longitudinal waves, because as I've mentioned a couple times now, you can have this interference happen in these different types of mediums with different types of waves. It could be in a string, it could be water, it could be sound. Sound, we're going to talk more about later specifically about sound, but sound is a longitudinal wave. And we can absolutely have constructive and destructive interference with that type of wave as well. And it's going to look a little bit different because the waves, longitudinal waves, are represented by areas of compression and areas of rarefaction, which we've looked at already. And so if you look here, you can see the same idea. Okay, if they line up where your compressions are lined up with compressions and rarefactions are lined up with rarefactions, just like with crests and crests and troughs, if they're lined up with the same parts in phase with one another, you can get constructive interference. Whereas if they line up so that they have opposite parts of the wave, your compressions lined up with your rarefaction and vice versa, then you're going to get destructive interference. So if you look at these two lettered images here, A and B, you can see in letter A that their compressions are lined up with the rarefactions and that the rarefactions are lined up with compressions of the other wave. And you can see the resulting wave looks like it's at equilibrium. They cancel each other out and everything's evenly spaced. Whereas if you look at letter B, those compressions are lined up with one another, and that's going to add together to give you areas of even greater compression and areas of even less density where those rarefactions are. Okay, so you can see that as well with a longitudinal wave.
This is a quick reminder.
Okay, so again, you can see these add up in the same way. So when you're looking at image B, you have those areas of high density give you even greater density, and the areas of low density give you even less density or even lower densities. So again, be able to identify it as well with these. Now it's a little easier if to add them and see if it's lined up, if they're actually shown on top of each other like this, because you can tell what lines up and what doesn't, rather than being next to each other like the other two were. So if I take a look at these, again, same idea. I have two different longitudinal waves here, and I have two different points labeled A and B. Okay, so at point A, Garrett, what do you think's happening here? Do you think this is going to be constructive or destructive interference?
Deconstructive.
You just mixed the two words together for me. Are these the same? Are these both compressions, or are they opposite parts of the wave?
They're both compressions.
Okay, so they're both the same part of the wave. Okay, and so if they're the same, they're going to add together. You're going to get constructive interference at point A. Okay, what about at point B, Alex? What's going to happen here?
That's destructive.
That's going to be destructive because this is a rarefaction and this is a compression. So those are opposite. They're going to cancel out either totally or in part. Okay, again. So again, if these are sound waves, where would it be loudest? Where would it be softest? What do you guys think? We haven't actually talked about that yet. Any guesses where you think it would be loudest? Yeah, where they're closest together. Okay, or if you're comparing the points, that would be point A. Okay, where you have the areas of compression, and especially where they're overlapping. And then you'd get softest if they were at point B because they would cancel each other out. Okay, and so that would give you, that's actually, I think I mentioned this the other day, but that's how noise canceling headphones work, is they use a microphone, a sensor to kind of collect ambient noise, and then they play the exact opposite of that so that it cancels it out. So it does this, like what B is showing. All right. Point C would be a little bit trickier if I gave you that, because it's kind of harder to see what's happening here at this point, which is why I didn't give it to you initially. But obviously it's going through a compression here, and here it's kind of in between the compression and the rarefaction. This might be closer to the equilibrium position, honestly. And so if you were doing that, if I asked you to add something like that, it might be easier to kind of overlay a transverse wave on top of it. That's typically what we do because it's easier to see them and how to add them. And as I said, it would be pretty close to equilibrium, and there it is. It's at equilibrium. But you can see what you would be adding better. It's easier to see it with a transverse wave. So you can draw them on top and put those crests in those compression areas and put those troughs in those rarefaction areas, and then it's easier to see how to add them. So if I do ask you to add two longitudinal waves and you're having a hard time with it, do something like this because it's easier to see exactly what you need to do. And at point C, you'd basically be adding nothing here from the second wave, so it would just be equal to the first wave's compression area. All right, so again, going back to wave behavior, I told you we were going to do a quick recap and then get into some stuff that we only barely touched on yesterday. So we did talk about this yesterday, that as waves travel through a medium like a string, we can look at how they behave when they enter a new medium like a thicker rope. Again, we talked about these boundary behaviors that occur when a wave goes from one type of medium into a different type of medium. And that could be a string into a rope. It could be sound waves moving from the air into the wall, okay, whatever. But you have these different behaviors that these waves will exhibit when they encounter a boundary, because it's not going to have the same properties. It's not going to just keep moving unaffected whenever it encounters a new medium. And so there are four possible boundary behaviors. We focused on reflection yesterday, but we did also mention these others. You can have diffraction, where the wave bends around the obstacle without crossing over it or through it. Transmission, where it goes through it. And when transmission happens, you can also have refraction, because the wave's going to have different properties as it travels through these different materials, and that can cause a change in its speed, a change in its direction, a change in its wavelength. All of those things can happen whenever you see refraction. So again, let's talk about refraction first. Refraction is the change in direction of waves as they pass from one medium to another. You probably already have that written down, but this is another good example maybe to copy down, because it's one that's kind of real world. If you've been to the beach, you've probably even seen this before. In fact, if you've been out in the kind of out past the most shallow part of the water and you're out there playing for a little while, you end up like down the beach, like 30 yards or something, and you're like, where's my stuff? And then you have to get out of the water and walk back. And it's because of the way that the waves are approaching the shore. They approach at an angle. But if you look at the wave fronts, you can see them here. This is just tracing on top of them at the bottom. They approach at an angle. You can see the crest of this wave. You can see the crest of this wave, and you'll notice that that angle changes as it gets closer to the shoreline. And so that's what's happening here is as these waves go from this deeper water into this shallower water, like where the sandbar starts, you're going to have a change in medium, and thus you're going to have refraction as they transmit into that new medium. And so what happens here is the path of the waves bends. That's typically what we see with refraction. That's what makes it easy for us to recognize it, is you look for bending. Usually that happens if the waves are approaching at an angle. It's always going to happen. But that refraction or bending of the path of the waves is also accompanied by a change in speed and wavelength of the waves, and of course direction in this case also, because we just talked about it bending. But you'll notice that they get, the distance between them changes, the speed of them changes, all these other things. But this is a very common real-world example of refraction, is ocean waves approaching the shoreline. And again, if you look at the actual image above, you can see them. I'm kind of tracing one with my cursor right here, but it is definitely at an angle. That's the one that's traced in the image at the bottom. And then if you look up here where they are cresting, they're almost parallel to the shoreline. So you can definitely see the bending whenever you look at it like that. And again, this is what's happening. You're going from this deep water medium into this shallow water medium, and it's causing, because you're going from one medium into another, there's different properties there, there's different temperatures there, but it's mostly about the depth of the water there that causes all of this to happen. Okay, so again, refraction only occurs when there's transmission. So the wave has to go from one medium into a new medium, and when that happens, that's called transmission, and it often is accompanied by refraction. Okay, but let's talk about transmission a little bit more. Transmission permits the passage of a wave with some or none of the incident wave being absorbed. Upon reaching a boundary, waves are often partially reflected and partially transmitted into the new medium. We saw examples of that yesterday where you had both of those happening at the same time. The transmitted wave may change speed and direction, so it may also undergo refraction. Okay, oftentimes it does, because the new medium has different properties typically than the original medium did. And so again, but transmission is just going through the new material. So if there's a sound, like there's a siren by the beach, and they'll sometimes play this for weather or things like that to warn people to get out of the water if there's something, or if there's a shark, there'll be a siren, and that sound can go through the water as well. Now we know, I'm sure we've all been underwater and heard something out of the water, and we know it sounds different. We know a lot of it gets absorbed, but there are different, again, properties of the wave when it goes into that new medium, so it's going to sound a little bit different as well. So here are some wave fronts approaching a new medium. So the new medium is represented right here, where it's going from one type of material into a different type of material, and you see the same thing with letter B. And so the question says, does the wavelength of the wave change when it enters a new medium? What about its velocity? What about its direction? And so if you look at image A, okay, it definitely speeds up whenever it goes into this new medium. But the thing is, the front of the wave reaches the medium before the back of the wave, and so the front of the wave speeds up, and then the back of the wave is still moving slower until it reaches the medium also, and then it also speeds up. But what that causes is it causes the wavelength to change. It gets stretched out. That's why it looks different over here than over here. Your wavelengths are different because when it approached the medium, again, the front of the wave sped up first, and the back of the wave was still moving slow. Okay, and so you get a change in velocity, you get a change in wavelength. This one does not change direction, though, because the wave is approaching straight on. However, if the same thing happens and it approaches at an angle like what is shown here in image B, then, again, same idea. If you follow one of these waves, I'll just pick the one that's kind of at the top where my cursor's at. If you watch it, the part that reaches the medium here starts to speed up, but the rest of it's still moving a little bit slower down here. And so it doesn't catch up with it until the whole thing moves in, but it causes it to bend because of the change in velocity that part of the wave is experiencing, but not the other part. And you still see that change in wavelength as well. Okay, so you'll see a change in wavelength. If it approaches at an angle, you're also going to see it bend. And again, in both of these show the change in wavelength and change in velocity, but when those waves approach at an angle, you're going to see bending. Again, this behavior is called refraction. Okay, it's the same thing we saw with the ocean waves a minute ago. It's actually opposite because they approached and then straightened out, but same idea. Okay, so again, this behavior is called refraction. Okay, importance of angle of approach, and this is what I was just mentioning. You're going to see a change in velocity and wavelength whether it hits head on or not. But if it hits at an angle, that means that part of that wave front is going to experience that change first, and that's why it causes the bending. So like in this case, these are actually opposite of what the images behind them show. These are both slowing down rather than speeding up, and that's causing the wavelength to get shorter. But this one, like this edge of this wave, is going to slow down first before this one. And because of that, this one's going to end up farther ahead this way, and that's what causes the bending. Okay, it's easier to see, I think, with the animation, but it's the same thing depicted here. But that's what refraction is going to look like. Okay, now again, just a misconception alert that we've already talked about before, but wave velocity depends on the medium. Okay, so the velocity with which the wave moves depends on the medium that it's moving to. We talked about this when I was discussing the FET because a lot of people think that frequency and velocity are the same thing, and they're not. But the top wave, if you look up here, is entering a new medium in which it slows down. So you can see it's moving faster over here, this green part, and then this new medium, it slows down, and that causes it to get compressed. Okay, down here, the exact opposite is happening. This new medium causes these waves to speed up. Okay, but if they stay in the same medium, this is not going to happen. It's the medium that determines the velocity of the wave. All right, diffraction. Okay, that's the only wave behavior we have left that we haven't really talked about much. Again, we've mentioned it, but you might want to write down some of these examples. Diffraction describes how waves bend or change direction as they travel around edges of obstacles. Guys, students very often mix up diffraction and refraction because both of them talk about bending. They are not the same thing. Okay, again, with refraction, you have a wave that goes into the new material, and because that new material has different properties, the wave changes speed and bends. In this one, the wave doesn't go into the new material, it goes around it. If I were to prop that door open and you were to go stand in the hallway, you could still hear me. Okay, it might be quieter, but you could still hear me because some of those sound waves are going to go through the opening of the doorway and they're going to bend in the hallway. I don't have to see you for you to hear me. Okay, the waves will bend around those obstacles, whatever those obstacles are. If you've been to a concert and there was a really tall person in front of you, you can still hear the music. It kind of sucks because you can't see it, but you can still hear it because the sound waves will bend around those obstacles. That's diffraction. Okay, so that's what's depicted here is Jill is talking or something, and these are the waves that are being emitted. And those waves, again, some of them are going to hit the wall and bounce off. Some of them might go through, okay, but some of them are going to go around the wall through this open doorway. So again, these waves that go through this opening, they don't go into a new medium. They're still in the same air. Okay, and so the medium stays the same, but again, as they go through, you get this bending, and even if you can't see each other, you can hear each other with these sound waves undergoing this diffraction as they go through the opening. Something else you might want to write down is the last part here. The amount of diffraction depends on the size of the obstacle or opening in relation to the wavelength of the wave. Okay, so the amount of diffraction that occurs, you're going to get more bending or less bending depending on how large this doorway is. Okay, if you have a very small opening versus a large one, the diffraction pattern is going to look different on the other side. So it's, again, the amount of diffraction depends on the size of the obstacle or the opening. In this case, it's an opening in relation to the wavelength of the wave. And here's what I mean by that. Okay, so you can see here visual examples of this, but if you read it, it says the amount of diffraction increases with increasing wavelength and decreases with decreasing wavelength. I didn't really show you that so much. These waves have pretty much the same wavelength, but this part, in fact, when the wavelength of the wave is smaller than the obstacle or opening, no noticeable diffraction occurs. So if you have a small opening, then the wavelength of your wave is going to be much larger than it. Whereas if you have a very large opening or a very large obstacle, then you're not going to have as much diffraction occurring. Okay, so if you look here, these waves don't bend very much because this obstacle is pretty large. However, this is a very small opening, and the diffraction is much more noticeable when you have a smaller opening or obstacle. You're going to have more bending on the other side. Okay, and that's what it says here. The obstacle is longer than the wavelength, so there is little diffraction. This one says the opening of the obstacle is shorter than the wavelength, so there is a lot of diffraction. But that's basically what we wrote over here. So again, you're going to want to write something down about the amount of diffraction increasing as those openings or obstacles get smaller, and that if you have a large enough obstacle that is larger than your wavelength, you're not going to see any diffraction at all, or at least it's not very noticeable. All right, which might help us answer this question. In our everyday environment, diffraction is much more evident for sound waves than for light waves. Anybody have any guesses as to why that might be?
So a lot of materials aren't like reflective.
It's not going to have to do with reflection here. That's a different wave property. Okay, diffraction's bending around it. Anybody know like what the wavelength of visible light is? Small. It's a good answer. It's measured in nanometers. It depends on the color. Okay, but 400 to 700 nanometers. Very small. Okay, sound, much larger wavelength. Okay, so because of that, again, if the obstacle is larger than the wavelength, it's not noticeable. Well, guess what? Most things are larger than 700 nanometers. And so we don't have noticeable diffraction because of that. The wavelength of sound, however, is much larger than the wavelength of light, so the diffraction is much more noticeable for sound waves. That's why I can hear you if you're outside in the hallway around the corner with my door open, but I can't see you. The light is not bending in here because that doorway is much larger than 700 nanometers. Okay, so again, something to keep in mind. We haven't talked a whole lot about light yet, so if you didn't know the wavelength of light, that's okay. But again, we're going to talk more about it in our next unit. So if we look here, diffraction that would occur in the situations below. So now I have waves approaching an opening, but those openings are two different sizes. Which one's going to have more diffraction, A or B? A. We just talked about that. Okay, so you're going to have more bending there than there. This has a greater curvature to it. Okay, so my diffraction pattern would look something like this in each of those scenarios. So you should be able to kind of identify from a multiple choice option, which would be, or rank them or something. But you could sketch them in your notes if you're trying to keep notes. By the way, this is slide 71 if I go too fast and you can't draw it fast enough. But again, that smaller opening is going to give you a greater amount of bending. That larger opening, you're going to have a smaller amount of bending. Or maybe not even noticeable at all. Okay, in this situation, again, it's going to bend around the obstacle, so you're going to get the same type of thing, except now you're only looking at half of it. But you're going to get these waves bending into this space over here. This one's trickier. However, we saw this yesterday. Okay, when those waves hit an obstacle like this, they're going to bend around it as well. And we saw this right here. Okay, we saw it with the ocean wave, little simulation with the island. It's going to start, well, it didn't start over, but you can see that pattern on the other side. Those waves, again, bend in to fill in this kind of shadow zone, and as they do, you get this really cool looking diffraction pattern as those waves start to overlap. All right, guys, so for the rest of the period today, you are working on your assignment 1302.3 Wave Behaviors Problem Set in My Open Math. So go ahead and make your way there if you haven't already done so. And that is what you're working on for the rest of the period. You're welcome to work together. If you run into something you're not sure about, ask your neighbor or ask me or look back at those notes. But go ahead and get to work, and if you have any questions, please let me know.